Today, let's explore the cubic function. F of x equals a times x squared times the quantity x minus 3k, where a is greater than 0 and k is greater than 0. This is a cubic function, which means its graph has the familiar downward then upward shape, with one local maximum and one local minimum. First, we'll find the derivative to locate the critical points. Let's expand the function before differentiating. F of x equals a x cubed minus 3, akx squared. Differentiating term by term, we get f prime of x equals 3 ax squared minus 6 akx. Factoring gives f prime of x equals 3 ax times the quantity x minus 2k. To find the critical points, we set this equal to 0. That gives us two solutions, x equals 0 and x equals 2k. At x equals 0, the function has a local maximum. At x equals 2k, the function has a local minimum. Next, let's find the x-intercepts of the original function. Setting f of x equal to 0, we see that x equals 0 is a root of multiplicity 2, and x equals 3k is another root. So the graph touches or crosses the x-axis at 0 and at 3k. Now, let's determine the point of inflection by computing the second derivative. Starting from f prime of x equals 3, ax times the quantity x minus 2k. Differentiating again gives f double prime of x equals 6, a times the quantity x minus k. When the second derivative equals 0, it indicates a potential maximum or minimum point of the first derivative. In terms of the original function, this corresponds to the point where the concavity changes, from concave down to concave up, or from concave up to concave down. Such a point is called an inflection point. Setting this equal to 0, we find the point of inflection occurs at x equals k. So, summarizing our key x values, a local maximum at x equals 0, an inflection point at x equals k, a local minimum at x equals 2k, and an x-intercept at x equals 3k. Notice the spacing between these important points. From 0 to k, the distance is k. From k to 2k, the distance is also k. From 2k to 3k, the distance is again k. Since a cubic function is symmetric about its inflection point, if we extend this symmetry one step to the left, we see that negative k, 0, k, 2k, and 3k are evenly spaced along the x-axis. Each consecutive pair is separated by the same distance, so the ratio of these intervals is 1 to 1 to 1 to 1. This shows a key property of cubic functions. By applying this proportional relationship, we can find cubic functions more easily. Let's work through a simpler example. We are asked to find a cubic function that satisfies three conditions. Its leading coefficient is 2. It has a double root at x equals -1. And the distance between the x-coordinates of its local maximum and its local minimum is 4. To solve this problem, let's apply the proportional relationship of the x-coordinates in cubic functions, the 1 to 1 to 1 to 1 spacing we just studied. This means the important points on the x-axis, the local maximum, the inflection point, the local minimum, and the intercept, are equally spaced. Each step has the same length. Since the local maximum and the local minimum are 2 steps apart, and the distance between them is 4, one step must be 2 units. Now let's consider the 2 possible cases. Case 1. (x equals -1 is the local maximum. Starting from -1 and moving right in steps of 2, we find the inflection point at x equals 1, the local minimum at x equals 3, and the next intercept at x equals 5. Therefore, the function is f of x equals 2 times the quantity x plus 1 squared times the quantity x minus 5. Expanding, the product becomes x cubed minus 3x minus 2. Multiplying by 2 gives the polynomial form f of x equals 2, x cubed minus 6, x minus 4. Case 2. (x equals -1 is the local minimum. In this situation, the sequence of equal steps extends to the left. The local maximum is at x equals -5. The inflection point is at x equals -3, and the other intercept is at x equals -7. Therefore, the function is f of x equals 2 times the quantity x plus 1 squared times the quantity x plus 7. Expanding, we obtain x cubed plus 6x squared plus 9x plus 4. Multiplying by 2 gives f of x equals 2, x cubed plus 12x squared plus 18x plus 8. So the cubic function that satisfies the given conditions can be written in either of these 2 forms. F of x equals 2x cubed minus 6x minus 4, or f of x equals 2x cubed plus 12x squared plus 18x plus 8. Both functions meet all the requirements.